So while we're opening to page 35, we'll take our quick look at the ever-dwindling calendar. Almost done. So today we're going to talk about Taylor series. Last class we talked about Taylor polynomials. Only difference between last class and today, the polynomial stops after a finite number of terms. Today we're going to let these things go forever like series do. Next class, stuff to do with finding and applying Taylor series. Next class, project 8 is due. That's the last math project of the semester, so hopefully we're making good progress on that one. Also next class is our last quiz, but again, we'll spend the first 20 minutes of, well, we'll spend the quiz time of the class doing it with your neighbors, all right? Same as the last couple of quizzes. Okay, and then Monday is the review day, and then Wednesday is the test. So 1 week from today is our third test. Any questions on the calendar? Okay, so let's go ahead and start again on page 35. And we begin at the top. And we will start with Richard. Okay, so we have seen this monstrous formula before. We saw it last class. The basic idea is you got to take a derivative. You got to plug in the number a that's given as part of the problem. You got to divide by the factorial. Which factorial do you divide by? Is whatever the power is, whatever that derivative was, n. And then you got to multiply by the thing that makes it look like a polynomial. All of this stuff is just a constant. And you stick that in front of finally the variable finally appears, it's x. X minus whatever the a was, it's the same a. And then you got to raise it to the right power. What's the right power? Is n, the same derivative you took, the same factorial you divided by. So we've seen that, but today what we're going to do is let this thing go forever instead of stopping it at some finite number of terms. So let's go to David for number 2. Okay, so a small little detail there, but if it happens that the value of a is 0, then it is a Taylor series, but it's got a special name. It's called a Maclaurin series named after somebody else. Okay, so let's give this a shot. The process is the same one that we followed last class. So we're going to write here f of x. We're going to write f prime of x, f double prime. And you need to go as far as you go. You have to go as far as you need to find the pattern. So let's just go 3 derivatives, and if we need more, then we'll find some more. Yes. Yeah, I mean, we did e to the 2x actually last class, and we saw the first derivative was 2e to the 2x, then 4e to the 2x, and 8e to the 2x, and you guys actually did generalize. You put 2 to the n, and it does happen to be a geometric in e to the x, but you came up with a formula, 2 to the n, and you made that very general thing. So here the derivatives are even easier. Next thing to do is to plug the magic number into all of these derivatives. What's the magic number in this problem? Is 0. So we need f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. 0 is given. It's part of the problem. You don't have to make it up. Okay, what are each of these things equal to? 1. Okay, then we have to take those magic numbers and divide by the right thing. What's the right thing? It's the factorials. So we're going to divide. I start at the bottom just so I don't mess up my counting, but the bottom one I divide by 3 factorial, then going up 2 factorial, 1 factorial, and 0 factorial. Okay, so we divide by the right factorial. How much is 0 factorial? is 1. It's just a definition. So the first term there is 1. Next term, also 1. Next one, it's a half. And the last one here, 1/6. And then next to each of these guys, we finally get to multiply by x minus a. What do I put instead of x? 0 for x? We put x. That's kind of a trick question. The x actually gets copied. What do you put instead of a is 0. And I asked that trick question because in the problem it doesn't say a equals 0. It says x equals 0. But you got to be aware of what we really mean. And then you put the right powers. What's the last power? Third, and then working up second, first, and 0. So we've got a lot of pieces. I don't think any of them is particularly hard. You just have to make sure you know where to put the pieces. Any questions on this? Joe? Yeah, so we'll put our answer down here at the bottom. E to the x equals, and I really mean equals. And now we're going to write out the series. We're just going to take those things that I wrote in green and black and put plus signs between them. What's the first term? It's just 1, right? Because the x to the 0 is nothing. So 1 plus. Next term is x plus 1/2 x squared plus 1/6 x cubed plus dot dot dot. You can write it as a sum. Let's see if we can figure out a general term, and then we'll write it as a sum. So the general term sure feels like we're going to have x to some generic power. It looks like they all are 1 divided by something. What's the thing that goes in the bottom? It's n factorial. And you just have to check one term to make sure that's accurate. There's a 3 on the power. There's a 3 factorial downstairs. It's perfect. It lines up. So that right there is our general term. I'll put dot 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 to say that we're going forever. And then at Joe's request, we can write this in sigma notation. It depends on the problem. On the project, I did ask you to write it in sigma notation, but it's my job to tell you what to do. Let's see. So then we just write that general term, 1 over n factorial x to the n. Where does n start? Yeah, it starts at 0 and then goes forever. What does it say? You gotta get the pattern. This particular question says, find the Taylor series including the general term. So that means go as far as you need to so that you can figure out what this is. Right? And if it's 3 terms, fine. And if you need more, then write some more. But do whatever you need to get that general term. So that's it. And what we have here is a way to write e to the x as a polynomial with infinitely many terms. And e to the x looks nothing like any polynomial I've ever seen. Right? We know that on the right side, e to the x grows faster than anything we've named, right? It grows faster than x, grows faster than x squared. It grows faster than x to the 100th. And on the left side, what does e to the x do? Asymptotes at 0. No polynomial asymptotes any place, so certainly doesn't asymptote at 0. But does it grow faster than 100 to the x? No, 100 to the x is also an exponential function. So because the base you named is bigger than the base e, then 100 to the x would be e to the x. Okay, so let's do the same thing we did the other day, and we'll just we'll get our series here. So first thing I'll just graph is e to the x. That's there. We've seen that before. And then we're just going to graph a few of, did we do this guy already? Did we do e to the x last time? Oh, we did e to the 2x is what we did. Okay. It's the same picture we were about to see, right? I mean, we saw it work last time, we'll just do a couple of terms. So it was 1 plus x squared divided by 2 plus x cubed divided by 6 plus, what's the next one? Divided by 6. What's the next term? X to the 4 divided by 4 factorial, that's 24. And then x to the 5th divided by 5 factorial. So that's enough. So, so you can see the x to the 5th polynomial is coming down here. It looks like it's quite good in here, quite good down there. So we're going to drag this around so we can finally see them pull apart. So it looks pretty good, you know, say from -1 to 2 or something like that.
Does this get harder to do if you're not centered at 0?
Harder to do if you're not centered at 0. Why do you say that? When you say the terms aren't going to cancel nicely, what do you mean?
Like the a sub whatever.
Yeah. So I think that the only change, if we were centered someplace else, like at x equals 2, these guys would all become 2's. So these things would all become e squareds. These guys would become e squareds. These guys would now become what instead of the 0? Would become a 2, and it's perfectly acceptable to just leave it as x minus 2 squared and x minus 2 cubed. So you don't have to expand or anything like that. You can just leave it. Okay, so next thing to do is right down here. We're going to find the interval of convergence for the series above. Now this series is particularly well behaved, but let's go ahead and find the interval of convergence. So this again will help you on the test, or on the project, I should say. So to find the interval of convergence, we definitely need to have the thing written in summation notation so that we can do our ratio test. So let's do the ratio test. Okay, so the ratio test says you take, which one? Do you take the current term divided by the next one, or is it next one divided by the current term? So this limit as n approaches infinity of the next term, an plus 1, over the current term. What's missing? Absolute value. That's important. Okay. We're going to copy that limit a bunch of times. And I'll just recopy the series that we had up above. It was 1 over n factorial x to the n. Is that what we wrote? Okay, so a sub n plus 1. We're doing this yellow highlighted thing here. All the n's become n plus 1's. So we got 1 over n plus 1 factorial times x to the n plus 1. What's that? We can put the x to the n plus 1 on top. Is that what we did before? Yeah, we absolutely can put it on top. We can't take the x out until we figure out exactly how many x's. Well, I guess you can't take the x out now because it does have an n attached to it, and n is changing. But we will cancel the x's and the n's will disappear. Downstairs here in green, we're supposed to divide by the actual, just the whole thing. But why don't we just go ahead and save a step and immediately multiply by the reciprocal. So times what goes on top, the n factorial, and on the bottom, x to the n. Any questions on where that came from? Okay, so if you buy that, take a moment to cancel. Some of the factorials will cancel and some of the x's will cancel. Cancel both. Okay, so let's figure out what's left here. Limit n goes to infinity. What happens to the x's? We have one more x upstairs, so there's going to be a single x upstairs. I'll put it there. And what happens to the factorials? So we just get the n plus 1 on the bottom, no more factorials, so that goes down here. So that's what we get when we cancel. Now what can we factor out? That x, because it has no n's in it and it is a constant in terms of that limit. 1 over n plus 1. And we don't need to put absolute value anymore because the n part is positive. It's always been positive. N is going to infinity. It was really the x that could have been negative, and it still needs the absolute value. Okay, what is this limit as n goes to infinity? It's 0. So the whole thing is just 0, which is one of our special cases. Is 0 very good or very bad for the ratio test? It is very good because 0 is always less than 1, which is the magic ratio test number. So why don't we give our favorite name to this limit? We'll just call it L. And then we can say here, since L is less than 1, the power series, which we'll just write in its entirety here, converges for what x's? For all x's, right? Because the limit is always less than 1 no matter what value of x you pick. Normally you'd have endpoints, you'd have to check, you'd have an interval, but in this case it's a special one. So typically you'd have something like this. Instead of having a 0 here, we call it a 2. And then you say, oh, okay, so that means that the absolute value of x times 2 has to be less than 1. So absolute value of x has to be less than half. So x has to be trapped between minus a half and half. And then you check the endpoints. But in this case, the question is, when is this inequality true? When is 0 less than 1? For what x's is 0 less than 1? It's true for every x. No, x could be anything. Even if x is 7 million, if you plug 7 million right here, this limit is still bringing the whole thing to 0, which is definitely less than 1. So no matter what x you pick, this series converges. I mean, there are 2 variables, but for the limit, there's just the one. It's n. You pick your favorite x, but x is a finite number. And then the limit will bring it to 0. So what that means is that the further out that we go on this thing right here, if I just typed in, like up here, I typed in only up to x to the 5th. But if I typed in more, then the x to the 5th polynomial would hug the e to the x for longer and longer and longer. It would converge to e to the x for any number that you want, meaning the more terms you get, the wider the interval of agreement, if that makes sense. The polynomial is going to match the e to the x better and better the further out you go, but that's not always true. It's true in this case just because of what we saw. The interval of convergence is all real numbers. Let's go to the next one here, number 4. Stephen. Okay, so that reminds me, there's one thing I wanted to do first. Let's take a look at this guy here. So I just made it an Excel thing right before class. What we have up here is that e to the x is definitely equal to this thing if you go forever. What that means is that e to the first is really 1 plus 1. I'm replacing all the x with 1s. E to the first. 1 plus 1, let me just write. So e to the first is equal to 1 plus 1 plus 1/2 plus 1/6 plus the next term. Oh yeah, 1 over 4 factorial 1/24 plus dot dot dot. And so I went to Excel and I just wanted to see how close we would get to E here. So this is the column that's just counting. What is this column? Those are the factorials. 1 factorial, 2 factorial, 3 factorial, 4 factorial, 0 factorial is the first one. What is this column here? What is that? That's 1 over, right? Because we're supposed to do 1 divided by the factorial. And then finally, in the last column that's mostly blank, what am I going to do? We're just going to add. So the sum of these two guys is this. What should be here if it's the sum of these three? Should be 2.5. So we'll just double click. 2.5 is that one. And if we keep adding, eventually it starts repeating like way down here. So 2.718281828. And then it changes, but it's repeating itself, I should say. And up here is where I just typed in, I asked Excel for e to the first power. So after only 12 terms, we've got it to agree to like the 8th decimal place.
Sorry to interrupt. My students want to know 106 again.
Yes. Yes. Welcome. All right. So there you go. E in a way that you've never thought of before. It's 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1 over every factorial, which is pretty nuts. I used to have a pencil when I was younger that that basically said E equals the thing that we just wrote down. But the disappointing thing, I was pretty proud to have this pencil, but the disappointing thing was that every time I sharpened it, the approximation got worse and worse. All right, next page, number 4. All right, so Steve read this one to us. We're playing the same game, but now we're going to do this function, ln of 1 plus x. And again, we'll do near 0. So let's give this a shot. So remember, we start by making our list of derivatives. How far do we go? I don't know. Far enough to get a pattern. So let's try going to double prime, and if we need more info, then we'll do more derivatives. What's the first derivative here? 1 over 1 plus x, which for the purposes of calculating more derivatives, might be easier to rewrite this as 1 plus x to the negative 1. Which means the second derivative is negative 1 plus x to the negative 2. I don't feel like I know what the pattern is yet. I can't tell just by looking at that. I'm thinking I need to go at least one more. So what's the next one? 2, 1 plus x, negative 3. You guys see the pattern? What's the next one? Negative 6. Negative 6, 1 plus x to the minus 4. Yeah. Yeah. So there's some easy parts in this pattern, and then there's the big hard part, and that's the number in the front. So the easy parts are that the power up here just keeps decreasing by 1 every time, right? Fair enough. The other easy part is what about the signs? They're alternating. We can capture that. But the hard part is the number in the front. I'll put it in green here. This is a 1. This is also a 1. Now it's a 2. Now it's a 6. But where have we seen those numbers before? 1, 2, 6. Those are the factorials that just keep popping up. The next one would be 24. So those are factorials in the front. Okay, let's go ahead and plug in what number into each of these guys. In this case, it's 0. How much is f of 0? Ln of 1, which is 0. Next term, 1, next one, minus 1, next one, 2, and then minus 6. And then how do we figure out what to divide by? It's the power with the factorial. So the last one is going to be 4 factorial. Rewrite which ones as factorials? Yeah, and that actually might be for where we're headed, because we still want to find the general term. We might need to write the tops as factorials to really identify this pattern. So the bottom one is really 3 factorial over 4 factorial, right? It breaks at 0. That's right, 0 factorial is 1. So what is this first coefficient? That's a 0. The next one is a 1. Next one, minus a half. Next one, 2 over 6, which is third. Last one, negative 1/4. That's right. And maybe we can, if we take Cole's suggestion here, we can see why we're not getting factorials anymore. We're getting just solitary 2, solitary 3, and solitary 4. It's because this 6 was really 3 factorial. And we have seen many times 3 factorial divided by 4 factorial is just 4, the next term.
Yeah, what, saying what is 0?
0, it's, yeah, I mean, yeah, I mean the pattern breaks at that one spot. He's right. Okay, so let's go ahead and stick in. I think we can squeeze in here the right x things. So this should be x minus what number? 0, and then this one is raised to the 3 or 4. It's 4. It's the factorial that's built in on the bottom. The factorials that came out of the derivatives, that was just a fluke. I mean, we shouldn't get distracted by that. So this bottom one is a 4th power. Previous one is a 3rd power, and work your way up. Okay, so then we can put it all together. ln of 1 plus x, that's the original function, and it is now approximated by the sum of all of those terms over there. First term, 0, we're not even going to write it. Next term, just 1x. Next term. Next term. Just 1/3 x to the 3rd. Next one. Okay, so that's just copying down everything we had with plus signs in between. But now we do want to be able to write the general term. That's part of the directions here. Okay, let's see if we can get the alternating part. How do we take care of that? Negative 1 to the, it's either n or n plus 1, depending on how we decide to start. Let's just leave it at that, and then we'll tweak it later if we need to. Let's see, I see n x to a power, so x to the n, and then they're all divided by n. It just perfectly works out. 4th power, divide by 4. So that looks like the general term. And now let's see if we need to tweak it. when n is 4, for example, then that's really negative 1 to the 4th, which is really what? Positive 1. Is the x to the 4th a positive term? No, so this isn't the right thing. Pick it with the plus 1 up there. See, we just picked x to the 4th to see if it matched up, and it didn't. So now it should be good. Good question. So if we write the sum, does it start at 1 or does it start at 0? So what value of n will give us that first term over there? Right, we see x to the 1st. So this guy starts at 1. It was a 0 and we didn't write it down. The only problem with putting 0 is that we have a divide by n in the formula. So the pattern just broke down on that one and we can't put a divide by n on that one. Yeah. Almost all the time n equals 0 is going to be the starting thing, except in a case like this where the first term just happens to vanish. Okay, so I said we were supposed to also find the interval of convergence. Now, I don't know about you, but I have no space left in this problem, so I'm not exactly sure where I intended for us to do this. Can we just do the highlights of the interval of convergence business? So you don't need to write it down, but if you wrote down all the details, it would be good practice later on. What test are we using? Ratio test. Every power series, we're using the ratio test. So we take, I'll write it here and then we're going to erase some stuff. You take the next term and then you divide it by the current term, but right away we'll change this to multiply by the reciprocal. The negative 1 makes no difference. It's inside of absolute value. What do we have left when we cancel the x's? We just have a solitary x upstairs, n and n plus 1. The x would come out in front of the limit. What is that limit when n goes to infinity? It's just 1. So that means that this guy right here is really x times 1. Which means the interval of convergence is all the stuff between negative 1 and 1. I know that was quick, and I know we wrote down hardly anything, but I trust that you can go through the same calculations we've done a few times last class and then today. And we get this. What else do we need to check technically? It's those endpoints. So for example, if we plug in x equals 1, let's plug it back into this red expression here. 1 minus half plus third minus quarter. That has a name. It's the alternating harmonic. But we've already seen, what does the alternating harmonic do?
So we have to plug in
Series. Yeah, you have to plug in both endpoints. Every time we do this ratio test, we got to plug both. I'm just doing one right now. Yeah, every time we do the ratio test on a power series. Yeah. Right, so if we plug in x equals 1, you get the alternating harmonic. We've already seen it converged. If you don't remember it, you can use the alternating series test and it will right away converge. So lots of jibber jabber and very little writing. I'm just going to put it converges at x equals 1, so we include that. If you plug negative 1 for x, what's the first term? It's a negative 1. Next term, is it positive or is it negative a half? It's still negative. Next term is negative a third. Next term, negative a quarter. They're all negative. So ignoring the negative, pretend they're all positive. What is it called? It is 1 over n, and that has a name. That's the harmonic. So does that converge or diverge? It diverges. So diverges at negative 1, converges at 1. So how about we take a quick look at what's going on in GeoGebra for this one. So here I'm going to change my formula. The original function was ln of 1 plus x. Maybe close your eyes and just try to picture in your mind what ln of 1 plus x looks like before you look at the screen. And then look up when you think you have some idea what's going on. All right, so I've typed in, I think I've done that right. This is the first 4 terms. So here's ln of 1 plus x. It's just ln of x, but shifted 1 unit to the left. And so then we'll hit enter here, and we get that. So this looks okay. You can see the polynomial. This is a 4th degree polynomial, so down on both sides. That makes sense. And it looks really good, actually, between what and what? Maybe minus a half out to a half. Looks pretty good. Okay, let's do a few more terms here. We can add these guys pretty easily. X to the 5th divided by 5, x to the 6th divided by 6, and we'll do one more, x to the 7th divided by 7. And now it looks better, right? Now maybe we're going out here to minus 0.6 and positive 0.6 or something like that. But no matter how many terms I go, it's going to look really bad once I get past what? 1 and minus 1. It's going to get really good on minus 1 to 1. But even if I do 100 of these terms, it will still look nothing like ln of 1 plus x outside of minus 1 to 1. Okay.
So if something has an interval convergence for all real numbers, then you're going to go with better approximation for all.
Yeah, you can approximate everything on a function where the interval of convergence is all real numbers. It'll just get better and better as you put more and more terms. But here, it gets better and better, but only on a focused window.
When the calculator is doing it, there's no point, so it doesn't need to have a range.
It doesn't need to have a range. It just needs to be close at one point. Yeah. All right. So let's think about. I think we did this already. Let me open this guy up real quick. Alternating harmonic. So we looked at this Excel document a few weeks back. This thing right here is doing what? That's alternating. Who are these guys? That's 1 over n. That's a half, that's a third, that's a quarter, that's a fifth. What's going on here? That's the alternating of that stuff. And then finally here, we're going to add up these guys. So if you add these 2 terms, what do you get? You get 1/2. If you add these 3 terms, 0.5 plus another 0.33, and you get this 0.833. And we saw that actually these numbers seem to be converging 0.68, 0.69, something like that. We went way, way down. I think we did like 10,000 terms in this thing. And you can see it really kind of honing in. It's not changing very much down here. And we got this crazy number. And then I said, for some reason that was unexplainable at the moment, that crazy number was ln of 2. So the alternating harmonic series converged for no reason whatsoever to ln of 2. But now we have every reason whatsoever for it to converge to ln of 2. What value of x did we just plug in to get the alternating harmonic series? We plugged in x equals 1, yes? That function approximates ln of 1 plus x. When x is 1, what do you get on the left-hand side? ln of 2. So it's not a surprise at all once you've got the structure underneath. Okay. All right, so we'll go to number 5 and then lots of time for group work. Tiffany? Okay, and so we saw that today, right? That was the pencil I was talking about. Angus? The third bullet. Okay, so why don't we see how far we can get in, say, the next 20 minutes on this Taylor series activity. Not sure exactly how far you'll get in 20 minutes, but get as far as you can. We might spend the last 10 minutes of class today just jumping to next class's material because we have a quiz and I don't want us to run out of time on Friday with the new material. moving there. So the reason we're skipping way ahead to page 45 is that in between the page you were just on and page 45 are the practice problems for test number 3, okay? So you can take a look at them later on. I'm still in the process of making the videos of me going through those practice problems. I hope to post them on YouTube later this week. I'm about 2/3 done with them. So on page 45, we'll go to number 1, and I think our reader is Chris. Okay, so let's take a look at this one. Now, I can't quite read it. It says e to the x cubed. Thank you. So to find the Taylor series for e to the x cubed, normally you would do exactly the process you guys just did, where you, now don't write this because we're not going to do this, but you'd do that, and then you'd say, okay, what's the derivative, and what's the second derivative, and you'd have to keep going until you found the pattern, right? And it's very time-consuming to just start from scratch, get all the derivatives, plug in the number for all those x's, divide by the right factorial, stick on the x minus the thing to the right power, and then add them all up. So the idea here is that we're going to try to start using some stuff that we've already built. So here is a fact that we know. E to the x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial. We proved that one today. Now the good news for you is that one exists on your reference sheet, page 1 of this packet. There's a few very famous series listed at the bottom. This is one of them. And so the idea here is that we can use this known series for e to the x to figure out the series for e to the x cubed. Instead of x, what do I want? X cubed. So we just replace all of those x's with x cubed. That's what we do. It's as simple as that. 1 plus, instead of x cubed. Plus, instead of x cubed, it's going to be to the 6th. Yes, I'll just write it as x cubed squared. Plus the next term, x cubed cubed. And then we'll just write a few of these guys with the x's mushed together. So x cubed squared is really x to the 6th. And then x cubed cubed, x to the 9 over 3 factorial, etc. Okay, you don't need to start from scratch if you are trying to find the series, trying to find a series that is the same as a series you've already got, but a different thing for x. This essentially allows us to do composition. We're now composing the e to the x function, which we know, with the x cubed function. And it's as easy as just plugging in x cubed for all those x's. To find the interval of convergence, well, that's also normally a very big problem. We would need to write the general term of this guy, and we need to do the ratio tests, the whole big limit calculation, endpoints separately. It's not as hard as that. All we need to do is figure out know what the interval of convergence is for the original, and then relate it to the one we want. This is also on your reference sheet. What is the interval of convergence for this? It's all real numbers. So what does that really mean? It means that it's any x that you want. This is kind of funny to write down, but I'll just put minus infinity to infinity. So that's the interval of convergence for this series. So the interval of convergence for the blue series, well, it's not x anymore. What is it? It's x cubed, which you then solve for x by cube rooting both sides. The interval of convergence for the thing that we want is also minus infinity to infinity.
Like you're just saying, it could have been a different order.
Yeah. So if this guy here had been like minus 8 to 8, if that was the original interval of convergence, what values of x will make it so that x cubed is minus 2 to 2? That would be the new interval of convergence, and it's easy. You don't need to start from scratch. So the the square root one is kind of funny. If we had this This was actually one of the group problems from the other day. You did the whole big ratio test and you end up trying to find x's that make x squared less than 1. And it feels like absolute value, you should do this plus or minus business. But then when you solve for x by taking a square root, you get imaginaries, which is a problem. So the way to handle this one is actually kind of cheesy, but it's easy. I'm just going to graph x squared, so very poorly. And then I'm going to graph y equals 1. And we're just going to ask you, when is x squared less than 1? Well, it's all the numbers between here and here, right? That's where x squared is less than 1. So that's from -1 to 1. So that's the answer to this inequality. Without taking square roots, without doing really anything other than just looking at a picture, we can solve that one. Okay, let's try part 2. ln of 1 minus 2x. Again, I don't want to start from scratch where I take all the derivatives and plug in and find the pattern, but I do want to relate it to a series that I already know. And again, on your reference sheet, that Taylor reference sheet, you'll find a series with ln, yes? It's not ln of x, what is it? Look, what is it? It's ln of 1 plus x. Look at the bottom of that page 1, you'll see a series with ln, and it says ln of 1 plus x. I've written it here for our convenience. It's this series, it's on your sheet. We don't have x in the problem we want. What do we have? We have negative 2x, right? Negative 2x. So that's all we do. Replace all of those x's with negative 2x. So the first one becomes negative 2x minus, what gets squared? Negative 2x gets squared plus what gets cubed? Negative 2x. And that's it. And so you can write out a few terms if you want to. Sometimes writing them out hides the pattern, but let's just write a few terms. Negative 2x gets squared becomes positive 4x squared. Divide by 2 becomes positive 2x squared with a subtraction in the front. So it's that. The next one, negative 2x cubed becomes minus 8x cubed. Divide by 3, minus 8x cubed over 3. And you can write out a few more terms. What have we lost? The alternating part. It turns out these guys are all going to be negative. And then the last thing for today is the interval convergence of this one. So let's first record from the reference sheet the interval convergence of the original. What is the interval convergence of the original? Negative 1 to 1. Open, closed. Okay, so this is again something we saw earlier today. Minus 1 to 1, open on one side and closed on the other. That's on the reference sheet. But instead of having x trapped between minus 1 and 1, what do we have? Negative 2x. So for us, we need negative 1 less than or equal to 1. But we have a negative 2x in the middle. Everybody see where the minus 1 and 1 came from? Just copied from the reference sheet. And then we solve for x, 1/2 here, minus 1/2 over here. What funny thing happens? You gotta flip that inequality, bigger than or equal to. And with very little work, that's the interval convergence of the new series. Yeah, the inequality just flips around. It keeps the equals if it still had it. Okay, sorry for going a little bit over today. We will see you next time with the quiz, which you will work on with your neighbors during the start of class.